Before moving to Lewis structures for 3 or more atoms, a brief word on electronegativity, which will appear later in our lecture. Electronegativity is the ability of an atom in a molecule to attract shared pairs of electrons. In other words, electrons get drawn towards the most electronegative atom. Electronegativity is smallest on the lower left-hand corner of the periodic chart and greatest on the upper right-hand corner of the periodic chart. Fluorine is the most electronegative atom. Before we do examples of Lewis structures for 3 or more atoms, let's review the steps. First, sum all the valence electrons from all the atoms. Get a total number of the valence electrons present. Second, the least electronegative atom goes in the center. Of course, hydrogen can never be in the center because hydrogen can only form one bond. But there's a shortcut here. Typically, the first atom in the chemical formula is in the center. Draw the central atom and atoms around the central atom. Then use a pair of electrons to form a bond between each pair of bound atoms. Arrange the remaining electrons to satisfy the octet rule. Again, except for hydrogen, which follows the duet rule. Arrange the electrons starting from the outside atoms towards the central atom. And finally, lone pairs of electrons may be moved between atoms to form extra bonds only to satisfy the octet rule. Extra bonds lead to double and triple bonds between atoms, for example. You will always do steps 1, 2, and 3. Step 4 and step 5 are not necessary. You use step 4 only when you have remaining electrons. And you use step 5 only when you need to satisfy the octet rule and you don't have any more electrons to add. Our first example is methane, CH4. We'll count the total valence electrons. 1 carbon atom and 4 hydrogen atoms give us a total of 8 valence electrons. The least electronegative atom goes in the center. Hydrogen can never go in the center. So carbon must go in the center. Around the carbon, we'll draw the other atoms. We're not worried about shape at this point, so anywhere else around the carbon atom, we'll draw the hydrogen atoms. Next, we'll draw the connections to show the bonds. Remember, these bonds represent a pair of electrons. So out of the 8 valence electrons available for bonding, we've used all 8 for bonds, which leaves us with 0 electrons remaining. This is the Lewis structure for methane. Let's do ammonia next, NH3. We'll count the total valence electrons first. 1 nitrogen atom and 3 hydrogen atoms give us 8 valence electrons. Hydrogen can never be in the center, so in this case, nitrogen will go in the center. Anywhere around the nitrogen, we'll draw 3 hydrogen atoms. And we'll draw the connection to show the covalent bonds. Here, there are 3 lines between nitrogen and the 3 hydrogen atoms. These represent the covalent bonds, or shared pair of electrons. 3 bonds means there are 6 electrons in bonding. That leaves us with 2 electrons remaining. We'll use those 2 electrons to satisfy the octet rule from the outside going in. Of course, here there are hydrogen atoms on the outside of the central atom. The hydrogen atoms satisfy the duet rule. Notice in the center, nitrogen only is sharing 3 pairs of electrons. Nitrogen wants to satisfy the octet rule. It wants to have 2 more electrons around it. Naturally, these 2 electrons remaining will go on the nitrogen. We use the 2 electrons, so we'll subtract 2 from our total, which leaves us with 0 electrons remaining. Let's do water next. Water is H2O. The total valence electrons are 1 oxygen atom with 6 electrons and 2 hydrogen atoms with 2 electrons. The total is 8 valence electrons available for bonding. Hydrogen cannot go in the center, so oxygen will go in the center, and the 2 hydrogens will go around the oxygen. We'll draw the bonds to represent the covalent bonds. There are 2 bonds present here, so out of our 8 valence electrons available, we've used 4 electrons for bonding. There are 4 electrons remaining. We'll use those 4 electrons to satisfy the octet rule from the outside going in. Again, hydrogen satisfies the duet rule. We'll use the 4 remaining electrons around oxygen to satisfy the octet rule for oxygen. Next, let's look at the organic molecule formaldehyde. The chemical formula is CH2O. Here there are 3 atoms present. We'll count the total valence electrons first. 1 carbon atom, 2 hydrogen atoms, and 1 oxygen atom give us a total of 12 valence electrons available for bonding. The least electronegative atom goes in the center. We can also use a shortcut here. Typically, the first element will go in the center. Around the carbon, we'll draw the 3 other atoms. And we'll add the connection to show the covalent bond. 3 bonds equal 6 electrons used. There are 6 electrons remaining. We'll use those 6 electrons to satisfy the octet rule from the outside going in. Hydrogen is satisfying the duet rule. Notice that oxygen is forming 1 bond, so it needs 6 electrons to satisfy the octet rule. Using 6 electrons, we have 0 electrons remaining. Notice we have a little problem. Carbon does not satisfy the octet rule, and there are no electrons remaining to add to carbon. Here we'll move to step 5. Lone pairs of electrons may be moved between atoms to form extra bonds, only to satisfy the octet rule. Here we are forced to move a pair of electrons from the oxygen in between the oxygen and carbon. This allows us to form the extra bond between carbon and oxygen. Notice that the new structure has the octet rule satisfied for both the carbon and the oxygen atoms. This is the Lewis structure for formaldehyde. This includes the double bond between the carbon and the oxygen. Let's next do an example of an ion. Here we'll do ammonium, NH4+. We'll count the total valence electrons. One nitrogen atom has 5 electrons, and 4 hydrogen atoms have 4 electrons. The total is 9. However, this is a cation, and there's a net positive charge. That means 1 electron has been lost. So from the 9 total electrons, we'll subtract 1, and that will give us a total of 8. Nitrogen goes in the center, surrounded by the 4 hydrogen atoms. We'll draw the connections to represent the covalent bonds. Out of the 8 valence electrons available, we've used 8 for bonding, and 0 electrons remain. Here's an example of SO2. We count 18 valence electrons total, 6 from 1 sulfur atom, 12 from 2 oxygen atoms. The sulfur goes in the center, surrounded by 2 oxygen atoms. Here are the 2 connections showing the covalent bonds. 4 electrons used in bonding gives us 14 electrons remaining. We'll use these 14 electrons to satisfy the octet rule from the outside going in. Clearly, each oxygen will take 6 electrons. That means we use 12 out of our 14 electrons. That leaves us with 2 remaining. Those 2 electrons will go into the center on the sulfur atom. That leaves us with 0 electrons remaining. Here, sulfur does not satisfy the octet rule, and there are no electrons remaining to add to sulfur. We'll have to move a pair of electrons from one of the oxygen atoms to in between that oxygen atom and sulfur atom. In this example, you can move a pair of electrons from either oxygen atom.